Fred. How you doing?
I'm doing well, sir. Thanks for joining us this afternoon.
Well, I appreciate you asking. This is for Navy Forum, right?
It is, and I feel like I know you a little bit, even though I've never met. Don Walsh is an old friend of mine.
Right, yeah. Don's great. I actually met, he might not have mentioned it, but I actually met Don in 1988 when he consulted for me on The Abyss.
Oh, okay.
When he called IMI, I think he probably still does.
IMI, yep, that's it.
And down in Long Beach or someplace. No.
Actually, it's out in Oregon.
It is, yes. At the time, it was in Los Angeles.
Oh, okay.
He drove someplace down there, and I went down, and I knew who he was, of course, and was slightly or greatly in awe, and I just started asking him questions about how stuff worked in deep ocean technology, and he had read the script and broken it down, and was incredibly helpful on that movie.
Well, he's a great guy. Well, I think I'm going to start off here. I think our audience would be interested to know what lessons you might have learned while designing and building the Deepsea Challenger that actually might apply to today's submariners.
Yeah, well, I think we had to approach it from the ground up, because the syntactic foam that was commercially available, that was supposedly full ocean depth rated, turned out to be in yield at the working pressure of 16,500 psi. So we had to design our own syntactic foam, and from that we also had the goal of using the foam structurally, which hadn't been done. Like your typical work class ROVs and research submersibles have usually a metal frame, might be aluminum, might be titanium, and then the foam is kind of just clamped on top of it as a kind of flotation jacket. And we knew that wasn't going to work because everything gets really marginal when you're diving at those pressures. The density of the foam has to go up in order to resist the pressure, and so your flotation gets significantly heavier, which not only impacts your sort of dry weight of the vehicle for handling it on the surface and launching and recovering it, but it impacts your kind of efficiency margin at depth. So if you've got a negative pressure boundary, the pilot sphere, and it's weighing, ton and a half negative, and you're using high density foam to try to float it back to the surface, you wind up, it's almost like the rocket principle, if you're familiar with that.
Yes.
In rocketry, the mass of the propellant relative to the payload starts to get really disproportionate. Well, in this case, it's the mass of the flotation relative to the payload. The payload being either me, the pilot, or the science package, which was the manipulator and so on. So we had to try to save weight wherever we could, and one of the ways we did it was by using the foam as the actual structural member of the sub. So we designed this big core beam and made it out of syntactic foam covered with composite laminate. My initial concept for it was that it would be like a glue-lam beam with layers of syntactic interleaved with carbon fiber composite, so that it would be a big, that it would have a lot of tensile strength, to resist bending moments. But it turned out that there were problems with that, and there were problems using carbon fiber in conjunction with the syntactic, because their bulk modulus was too different, and it would have delaminated. So we wound up not putting the composite on the inside. We just used it on the outside as a kind of skin, both for toughness and to prevent the initiation of cracking, kind of around the fasteners and things like that. So we had to find a composite material that would match the bulk modulus of the foam. And that took a while, and we did a fair bit of experimentation. We eventually wound up with a certain grade of polyester cloth, and we experimented with different resins and so on. So a lot of trial and error went into this, but we eventually, once we got our kind of material science down, then we built this big 4-ton beam that was about 20 feet long. That was actually the core structure of the vehicle. So there was no conventional chassis whatsoever, and I actually think that this is a very viable way to build deep vehicles.
Interesting. You had hydraulics problems in the first dive. Have they been rectified?
Well, we did did a series of 9 dives through our initial trials and into our full ocean depth dives. I did 9 dives, of which the Challenger Deep dive was actually, I think, it was actually dive 10, but I piloted the 9 myself. One was unpiloted. So we went progressively deeper, 1,000 meters, 4,000 meters, 7,000 meters. The hydraulics problem didn't show up until we got into the 7,000 meter range, and there was some problem with the way it had to do with the differential valve pressure and the way there was a reservoir that was overpressurizing, and it actually blew out the wall and allowed seawater into the system. So then we had to strip down hydraulics and repair it. And the same problem showed up again. A similar problem showed up again on my Challenger Deep dive, where a hose fitting failed and we got seawater into the system, into the valve pack. But these are kind of pretty conventional hydraulics problems. The irony for us was that so much on the sub was designed and built by us from scratch. I mean, virtually every printed circuit board on the exterior of the sub, the driver boards for the thrusters, because it was all PBOF, it was all oil compensated, and it all had to work at full ocean depth. So we designed and built our own thrusters. We designed and built the driver boards for the thrusters. We designed and built the lithium-ion batteries. And there might be something that has application in the battery, so I'll come back to that. The battery management system, we had to create all our own PC boards, and everything had to be pressure tolerant. And the one thing that was kind of off the shelf on the whole sub was the manipulator arm and the hydraulic system. And so we kind of trusted the guys because it was a proven system. It had been on other submersibles. And all they did was gross up the compensator volume because we were going deeper. And it turned out that wasn't an adequate solution. We basically had to re-engineer the system on the fly. Ultimately, by the end of the program, I did 3 more dives. The sub did 3 more dives after the Challenger Deep dive, and we actually got the hydraulics kind of all smoothed out. But the point of that kind of long ramble is that it was the problem we weren't looking at that proved to be a big problem, because we had sort of thought, well, that's okay, that's off the shelf. All the stuff we built from scratch, obviously, we were scrutinizing, we were testing, and we had pretty rigorous test protocols. I mean, we could have used another year. There's no question about that. But I think there's probably never been a program where people couldn't say that.
Well, I have been doing a lot of reading about what some have referred to as the race to the Challenger Deep. Where are the other projects? What stages are they in? Do you know?
Well, I think basically, I don't think there ever really was a race. The only clock I was trying to beat was my commitments to other projects. So I really had to finish this thing at the latest by first quarter of this year. And we actually kind of rammed into another project, which was the release of Titanic 3D. And I had to actually go off and do some press for that, and then come back and finish the expedition, which was a real kind of meltdown. It wasn't ever intended to happen. So I didn't feel we were ever racing them. I felt, we were just sort of racing the normal clock. Once you get a big team on payroll, every week costs you money. And so it was really just trying to get the project done in an efficient manner. In terms of the other guys, there's the Branson team, which is Chris Welsh is the chief pilot, Graham Hawks is the designer. You'd probably have to talk to them about where they are. From what I understand, they haven't pressure tested their new. They were having some interface issues between the fused quartz front hemisphere of their pressure vessel and the titanium seat, and they needed to pressure test that. Haven't done it yet, so they don't have a proven pressure hull yet.
The Navy was once heavily involved in deep submersibles, but now not so much. Why do you think that is?
Well, I think I think for military applications, they're using the ocean primarily to conceal the movement of the vessels, so they don't really need to go that deep. Just need to get they need to move silently. So I think they put their money on, anechoics and quiet propulsion systems and countermeasures and all that sort of thing that were more appropriate to them. I think there was a period of time where they thought, well, we need the capability in case we lose a sub, we need rescue capability. So I think that, the DSRV program came out of some of the early research for research submersibles. But I think the Navy was pretty pragmatic about it. We'll just build what we need. But I think they kept a hand in the research community via the Alvin program and some oversight and funding of that with Woods Hole. But I don't know the ins and outs of that part of it. I don't know what the Navy would do if they lost something at Hadal depths and had to go get it back. I guess they'd probably have to call us unless they've got something that we don't know about, and I suspect they probably do.
After Walsh and Picard made their dive in the Trieste in 1960, it didn't receive much publicity. Why do you think it was mostly kept secret and the space program got all the attention?
Well, it's interesting. I mean, I think it certainly would have been the kind of flags and footprints accomplishment that should have been trumpeted. I think it was the public's imagination was more captured by space and by the space race. It wasn't until later in the 60s that underwater got I think, kind of sexy and more in the public imagination. It was almost too much too soon. It was too abstract. They didn't appreciate the problem. And, when Cousteau came along and he had the little diving saucers and things like that, people started to wake up that there was this whole ocean that needed to be explored and understood. I don't think they were thinking about it in the 60s. I think it was really more of a post-World War II mentality that the ocean was a place where you fought, where ships sank, and where you were fighting the U-boats and that sort of thing. And it wasn't thought of as this sort of mysterious, scientifically interesting place.
What would you say the biggest difference between diving now and, say, 52 years ago, or even between now and your first dive on the Titanic?
I think probably not much has changed in principle since syntactic foam was brought in and research submersibles sort of took on their basic configuration. What's interesting between Trieste and the Deepsea Challengers is what's the same and what's radically different. Obviously what's radically different is they were using gasoline for flotation, which was a clever and even elegant solution for its time, because syntactic foam hadn't been invented yet, certainly not refined to the degree that it is now. But it was made completely obsolete, that concept, the second that in the early 60s they developed syntactic foam for the first time. So the idea of a big gasoline balloon is a dinosaur idea. On the other hand, the idea of a steel sphere with an acrylic port set in a conic frustum seat is basically what we did. The only difference was they had a separate hatch, and we incorporated our hatch and our port together, so that the hatch seat actually became the conic frustum seat of our port. They had a flat acrylic port. We did a dome port because we had experience with dome ports from the 6,000 meter camera housings that we designed and built, for 3D shooting and that sort of thing. So, we kind of didn't want to go as radical as the Graham Hawkes designs, because I didn't, I was mistrustful of ceramics because there wasn't enough data. When we started the project 7 years ago, there wasn't as much known about ceramics. And glass, I know the Navy had tried to build glass hulls at the China Lake project back in the early 60s, and it spent a couple of $1 million at that time, which would have been like $20-30 million today, and failed to get the glass to cool in a way that didn't create stress fractures. So I thought, all right, if we went to a glass hull, that might be a science project that could eat up 5 years of R&D and a lot of money, as opposed to working with steel. We built steel pressure vessels, and we sort of knew that was something that would be just barely within striking distance. Of course, at those pressures, the steel is just really starting to approach yield, and you have to design very carefully. And another big difference now is that we have computer FEA programs that are quite powerful, and you can quickly make changes to the design and and run those sims and look at the stress fields, and you can refine the design. You know, they were doing it all with slipsticks and model testing, things like that, back in the 50s and 60s, and it's remarkable that they were able to achieve the results that they did. But if you look at Trieste, you know, it's a big gasoline float with a steel sphere underneath it with an acrylic port. And what we've got is a big syntactic float with a steel sphere underneath it with an acrylic port. So the principles haven't really changed that much. In fact, we even ballasted the same way they did. They used a steel shot. It turned out to be almost exactly the same type of shot that we used. We used 3mm bird shot, and they used, I think, probably almost the same thing back then, just a whole lot more of it because their vehicle was about 10 times more massive.
Well, I got to change gears to the Titanic with the anniversary of the disaster coming up. Why do you think the Titanic still captures people's imagination?
Well, I think different people may be fascinated with different parts of it. You know, but they're, you know, I think it's almost the sort of the novelistic perfection of it. You know, the fact that it was the supposedly unsinkable largest ship of its time, if only by a few inches, you know, larger than its sister ship, the Olympic. You know, the kind of the arrogance and hubris of the guys that sailed it, you know, on a dark, moonless night into a known ice field with a pocket full of Marconigram warnings that there was ice ahead at full speed, and we're still lighting boilers and bringing them online in the hours right before the impact. I personally find it fascinating for the human stories and the fact that it, you know, unlike an air crash, you know, that's sort of over in an instant, that these people had, you know, 2 hours and 40 minutes to see their fate coming, and even in some cases to make choices, to step back from the lifeboat so that make a place for others, you know, or how the you know, sort of the morals of the times had the gentlemen standing back as the ladies and children were put into the boats and so on. And you know, so I think there's a fascination with this idea of death in slow motion. It gives people a chance to think about how they might have behaved under similar circumstances. Would they have, you know, would they be the guy that was like putting a shawl over his head, putting on lipstick, and trying to jump in the lifeboat as a girl, or would they have been honorable? Would they have been, you know, a heroic member of the crew, staying behind and you know, working the pumps or working the falls, you know, to save others, or would they have been the, you know, the crew members that at the first chance, you know, sort of jumped into a boat and rowed away, like the craven coward Hitchens, Quartermaster Hitchens, who was actually at the ship's wheel at the moment of impact, and later was in command of Boat 6, who refused to row back and save people. So you see the full spectrum of human behavior and human character, and I think certainly, you know, I think anybody in your readership is going to be fascinated with the ideas of character under pressure and in adversity.
Absolutely.
Yeah, and another thing that I'm sure your readership is fascinated by is the idea of crisis management and the command structure and how that worked and how it didn't work. You know, you had a captain who basically went catatonic. His officers immediately below him essentially took charge, and you've got First Officer William McMaster Murdoch, who was almost single-handedly responsible for saving about 2/3 of the people that were saved. He just, you know, sprinted into gear. He was getting these boats. We built the davits for our set. Actually had them commissioned and built by the same davit company that built them back in 1911 for the Titanic, the Welland Davit Company. So we actually got essentially real Titanic davits, and they are hard to operate. I mean, they you know, those lead screws turn very slowly. It takes two guys to crank them, and Murdoch was getting these boats in the water, boom, 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 one after another, and just jamming people into them. On the other side, they were under Lightoller. You saw a very different. Lightoller was a competent officer, but it was women and children first, which meant women and children only. The boats were being launched half full or less because he couldn't find enough women and children to put in the boats, and because he was hesitant to fill them and then descend them 5 or 6 stories down the side of the ship. But I have one other quick anecdote I want to share with you, and this actually ties back to the Navy in a nice way. Commander Jeff Stetler at the Naval Academy. He's an instructor there, and I worked together on and another a civilian named Park Stevenson who works in the private sector, but in defense contracts. The three of us worked together for about 2.5 years to develop a very, very comprehensive and complete sinking simulation of the Titanic, computer modeling, using some of the programs that Commander Stetler uses for teaching and so on. There's a program called Maestro and another application called Posse, and they're used for studying, stress strain analysis of complex structures, hulls and shell plating and all bulkheads and that sort of thing.
Is he still here?
Yeah, I think he's. Where are you?
Well, I'm on the grounds of the academy. We're in the old hospital.
I don't know if he's actually physically there today, but I mean, you should look him up.
Yeah, I should.
And he can fill you in on this modeling that was done. But here's the interesting outcome from it. I think he's about to publish a paper if he hasn't just done so on the findings. But it's not only is it the most complex and complete model of the Titanic that's ever been done, and inclusive of the progressive sinking simulation, it might well be, according to him, the most complex progressive sinking simulation done for any ship. And a really interesting thing came out of it, which is that every time we ran the sim with minute adjustments to the starting conditions, having to do with permeability and a bunch of other things that he can explain much better than I can, the ship would flood in a manner that initially followed eyewitness testimony, but within about half an hour, it would start to heal and then eventually get into a very strong lull of about 45 degrees. And it would, depending on input conditions and almost sort of randomly, sometimes it would lull to port, sometimes it would lull to starboard, which is counterintuitive because you would think it would always go to the side where the initial flooding was, on the starboard side. But that didn't happen because it equalized very rapidly in those forward holds. And then after that, it was just free surface effect. But it would always tip over to about 45-degree angle. And ultimately, in some of the sims, it would capsize before it sank. But usually it just got into this strong, kind of lulling condition. But that's not what happened. And we know that. We know there are very few events in history described more accurately than the sinking of Titanic, the 703 survivors. The question is why? And the conclusion that we came to as a kind of forensic panel meeting on this, of which Jeff Stetler was a member, was that it was the engineering team working in the machinery spaces, trimming the ship, frantically trimming the ship, to keep it as level as possible to allow the lifeboats to get off. Because, you can appreciate that as the ship changed trim down by the bow, the stern came up, and some of the aft boats, they were going down 6 or 7 stories with these falls, and so the ship had to be as upright as possible. So what I believe we were able to infer from these computer models is that the engineers, none of whom survived, actually are the real heroes of the night. And nobody knew this. Nobody even asked the question. You look at Andrea Doria hold on one side, same problem, free surface effect, ship capsizes. Costa Concordia, same thing. Titanic was only hold on one side to our knowledge, and yet it remained perfectly upright. Now we know that there was a lot of frantic activity down below, that watertight doors were being opened, that pump hoses were being run from pumps aft forward. We're not quite clear why, because they were being run into a compartment that wasn't hold. It's very possible that they were just moving water from one trim tank to another. We can't confirm this because there's nobody survived to tell the tale.
Well, you're talking to the members of the Naval Institute in this interview, and I'm just wondering what message you would send to those members to an organization that's been discussing subjects of the sea since 1873.
Sure. Well, look, my experience is very deep and very narrow with one ship. Actually, a handful of ships, but really primarily Titanic and Bismarck. And those two wrecks together really tell us a very great deal about how ships sink. A lot about marine architecture, and certainly a lot about wreck site forensics. And my message would be that there's still value in studying these wrecks, even though the technology is obsolete. We don't do riveted ships anymore. We've already learned so much from a century of steel ships sinking. But here you have a couple of classes, a couple of years of classes of mids, working in their spare time on these computer models, coming up with some conclusions that are still, I think, profoundly interesting now, and certainly have a real historical resonance.
Well, I think I've reached my time limit, Mr. Cameron. I really appreciate your time, and hope to run into you sometime soon.
Well, look, I'm happy to give you the time. First of all, just out of respect for the Navy and for what you guys do, and I'm glad I was able to bring to your attention what Commander Stetler is doing, and also, frankly, just because of Don Walsh and his contribution and the opportunity to make sure that the world remembers these pioneers. As you pointed out, that they didn't really get the ink that they deserved at that time. And one of our goals with this project, and the reason that Don was out there with me, and the reason that he was the first person whose hand I shook when I was coming out of the sub, is because we wanted to not only, make a case for the science in the Hadal depths and the new technologies, but also to make sure that the world remembers these pioneers, because it was a whole lot braver for them to get into a vehicle that was designed with a slide rule than for me to get into a sub that was designed with advanced computer modeling, at least in my book.
Well, thank you very much. You'll be interested to know a picture of that handshake is going to be in the next issue of our magazine Proceedings.
Great. And the only other thing I would shoehorn it in is that my goal in this is to promote deep ocean exploration. I don't own technology companies where I intend to make a profit off of the IP that was generated. I mean, I think we came up with a few new tricks in the design of this sub, but I consider it pretty open source. And if there's anybody that is working on a vehicle program and wants to know what we did and how we did it, I'm more than happy to share the technology.
Appreciate it.
The foam, the structural engineering, the battery system, which I think was unique, because I know that a lot of people have been struggling with how to make lithium-ion battery systems that are ambient pressure systems, PVOF, oil compensated batteries, make them safe. And I think we came up with a way to do that we're pretty happy with. So if anybody wants to reach out, I'm more than happy to be available for that.
Okay, we may just take you up on that.
Okay.
Thanks a lot, sir.
Yeah. Okay, Fred. Thanks a lot.
Thank you.
All right. Bye-bye.
Bye-bye.